Welcome to the fifth lecture for the class 11th mathematics chapter 4 of complex numbers and quadratic equations. So we are still continuing with the different kind of algebraic operations on complex numbers. So either one single complex number or a combination of more than two complex numbers. So till now we have seen how we can apply the addition, subtraction, how we can find the product or as well as quotient between two or three complex numbers. We also saw how we can find the power of one single complex number. We saw power of I, how it varies as per the changing the k or changing the power of the I. So there were certain rules that were that have to be followed when we try to find the power as well as the square root of a negative real number. Okay, so these are the some of the things that we saw till the previous class. So now we will try to prove different kind of algebraic identities that we normally use. So we know few of the identities when we have done the normal in linear algebra, or when we dealt with only real numbers, not the complex numbers as a whole. So these are the very standard identities, but we will see how they are applied on complex numbers. And also we will try to prove the identities while using complex numbers, and also some examples on how we can solve with complex numbers. So few like the first three identities that we will be using deal with two complex numbers. Okay, so you have Z. Okay, so you have two complex numbers, Z1 and Z2. So mostly suppose Z1 is equals to A plus B, and Z BI, and Z2 will be C plus DI. Okay, so these are your two complex numbers. Now we will see for each of these complex numbers how we can simplify the left hand side, and we will try to prove how the left hand side is equal to the right hand side. So the first one that we had is when we square the sum of two complex numbers. Okay, so suppose this is the identity, and we know in general, when you have a plus b the whole square, so we have a square plus 2ab plus b squared. Okay, so this is the general identity that we use. So let's see if it is if the proof for the in the terms of complex numbers can be proven. So we had learned about the kind of we can separate the power into two individual terms. So we will do this in terms of, okay, so now it is easier for us to simplify when we write it in the separate terms. So now using distributive law that we had used when we were doing addition, and as well as when we were trying to do when we had seen how multiplication, there are a few rules which are followed when there is when we have to multiply two complex numbers. So using those rules, okay, so we segregate the terms. Okay, so this is due to the distributive law. Okay. Now, as how we proceed with the multiplication of between complex numbers, so we will find z1 square plus z2 z1. Okay, and when we expand the second term, we will get z1 z2 plus z2 square. Okay, so finally we get z1 square plus these two are the same. If you remember the associative law that we had, so z1 z2 is equals to the commutative law, z1 z2 is equals to z2 z1. So they are actually the same terms. So we can write it as z1 z2 plus z2 square. Okay, so this validates and proves the identity, and you can see that this actually follows the general form of the identity a plus b the whole square. Now let's see an example. So suppose you have z1 is equals to 6 plus 3i, okay, and your z2 is equals to 2 plus I. Okay, so these are your two complex numbers. So to get like if you have to solve for this, okay, so what will be z2 plus z1 plus z2 the whole square. Okay, so you can write this as 6 plus 3i plus 2 plus I the whole square. Okay, so now we will try to solve it in the form of the identity. Okay, so the identity that we are using here is z1 square plus 2 z1 z2 plus z2 square. Okay, so let's expand this we'll expand this the terms over here, and we will write it in this form for the identity. So you will have 6 plus 3i squared plus 2 3i plus I is 2 plus I the whole square. Okay. Now these individual terms you can solve in the form of a plus b the whole square. Okay, so it would be in the similar form that you can expand and simplify. So what we get is, if we first expand this, we will have 6 squared, so that is 36, and 2ab, so that is going to be, so 2ab will be 6 into 3i, so that will be 89, 89 into 2. So again 36i, and over here you have to get 3 squared I squared, so that will be 9i squared. Okay, so we expanded this. Now for the middle term, you can keep 2 out for now, and just follow the normal distributive law for how multiplication. Okay, so this will be so this will be 12 plus 6i plus 6i plus 3i squared. Okay. Now again, we expand 2 plus I the whole square in terms of a plus b squared, the whole square. So we will write this as 4 plus 4i plus I squared. Okay, so this is after we have expanded all the terms and we have multiplied the middle term. Now we'll take off the brackets and simplify it further. So 36 plus 36i. Now over here we know that I squared is equals to -1. Okay. So the sign for the coefficient 9 changes because we are multiplying it by -1 now. So it's 9 plus multiply this entire bracket by 2. So 24, and 6i plus 6i will be 12i. So again, you multiply that by 2. So you get 24i. Okay, again over here, this will become minus 3 because I square is equals to -1. So minus 3 into 2, so you have minus 6 plus 4 plus 4i, and you have I squared over here, so this becomes minus I. So now what we do is we take all the whole numbers on one side, whole real numbers on one side, and we will club the imaginary numbers on the other side. So you have 36 minus 9 plus 24 minus 6 plus 4 minus 1. Okay, so all the real numbers we have taken on the other side, then we put plus, and we take all the imaginary numbers to the other side. So 36i plus 24i plus 4i. Okay, so if you solve the entire thing, what you are remaining with is 48 plus 64i. Okay, so if you take out the highest common factor out, so you get 16, 3 plus 4i. Okay, so this is the answer that you get for two complex numbers, and the whole squared of when you want when we add this, when we add the two complex numbers. Okay, so over here we are using the identity to get the solution for this term. Okay, now we'll move on to the next identity. So similarly, how you have a plus b the whole square. So now we will solve for z1 minus z2 the whole square. So in a way, we know we will try to prove that z1 minus z2 the whole square is going to be equal to z1 square minus 2z1 z2 plus z2 squared. Okay, so we will try to prove this. Now again, for the LHS part, let's write it in the form of z1 minus z2 multiplied by z1 minus z2. Again, using your your distributive law, we can simplify this as z1 minus z2, z1, and then negative 1, z1 minus z2 multiplied by z2. Okay, now we open up the brackets and we multiply it. Then you have z1 squared, then you have z2 z1, and similarly you have z1 z2, and you have over here, since you have both the negative signs, so when you open it up, you get plus z2 squared. Okay, now similarly, where we have the commutative law that z2 is z2 z1 is equal to z1 z2. Okay, so finally we can write it as minus 2 z1 z2 plus z2 squared, so which is your RHS. Okay, so this is hence proved. So now let's see an example. We'll try to solve the similar example that we took, like z1, where z1 is x plus 3i and z2 is 2 plus i. We will see what answer will we get if we apply this identity. Okay, so again, your z1 is equals to 6 plus 3i, z2 is equals to 2 plus I. So we want to know what is z1 minus z2 the whole square. Okay, and we remember the identity z1 square minus 2 z1 z2 plus z2 square. Okay, so let's write this as 6 plus 3i minus 2 plus I the whole square. Okay, now we use the identity given to us. You have 6 plus 3i the whole square minus 2 into z1, z2. So 6 plus 3i, 2 plus I, and plus you have the z2 squared. So that is 2 plus I squared. Now again, you expand the first and the third term with respect to a plus b the whole square as a square plus 2ab plus b squared. So again, it will be similar to what we got in the previous example. So you have 36 plus 36i, 36i plus 9i squared. Okay, and 2, putting 2 out, uh, you have 12 plus 6i plus 6i plus, this will minus, okay, minus 3, or you can first write it as 3i squared plus 3i squared. Okay, and you expand the third term also. So you have 2, this will be 4 plus 4i plus I squared. Okay, you expand and you substitute for the I squared values everywhere. Okay, 36 plus 36i minus 9. Then you expand this bracket, so you have minus 24. Over here, this will be 12i, so this is again minus 24i. And this becomes minus 3. So minus 3 into minus 2, you have plus 6. And then 4 plus 4i. And over here, this will be minus 1 again. Again, you take all the real numbers to one side. Excuse me, 1 minute. So you have 36 minus 9 minus 24 plus 6 plus 4 minus 1. Okay, then you take all the imaginary numbers to the other side. You have 36i minus 24i plus 4i. Okay, so you calculate it, you get 12 plus 16i, and you can further reduce it by taking 4, 3 plus 4i. Okay, so this is your answer to the this term. Okay, so when you are giving two complex numbers and you are asked to get the whole square of their difference, okay, and you have to use the identity, it becomes simpler for us to use. And even when you get the complex kind of examples where you have to solve these, so you will see that it gets easier if you use the identities that are proven over here. So now let's go to the other identity that we had. So okay. So the next identity that we had was z1 plus z2 multiplied by z1 minus z2 is equals to z1 squared minus z2 squared. Now, if you say this is of the form where you have a plus b, a minus b becomes a squared plus, a squared minus a squared minus b squared. Okay, so this is of this general form. So now let's again we try to see how the LHS can be proven to can be proven equal to the RHS. So the LHS part that we have is Z1 plus Z2, Z1 minus Z2. Okay, Again, using the distributive law that we had established for when we were finding products between two complex numbers. So this you can separate out. So Z1 plus Z2 multiplied by Z1 and minus Z1 plus Z2, Z2. Okay, so you expand, then you get Z1 squared plus Z2, Z1 and minus Z1, Z2 minus Z2 squared. Okay, now over here again, as per the commutative law that we have, that is Z1, Z2 is equals to Z2, Z1. So this we know. So this actually they cancel each other out. So what you are left with is Z1 squared minus Z2 squared. So which is equals to your RHS and hence proved. Okay. This is one of the easiest kind of identities that you can remember and that you can work upon. Okay. So let's see an example for this again. So you have Z1. We will take the same example. So 6 plus 3i and Z2 is equals to 2 plus I. Okay. Now, since we know that Z1 is Z2 and Z1 minus Z2, we want to know what is the answer for it. Okay, so you can directly, you can substitute it in the form of the identity as it is mentioned here. Okay, so Z1 plus Z2 and Z1 by minus Z2. So you can write it directly as Z1 square minus Z2 square. Okay, so now you have two options. Okay, so if you can, directly apply the identity for, for each of the terms. Okay, so either you expand the individual terms using a plus b, the whole square is equals to a square plus 2ab plus b squared. Okay, or you can, simply go with the form with Z1 plus Z2 multiplied by Z1. Okay, and then in that sense. So since we are trying to use the identities, so we will expand each of these terms with respect to the identity and we will solve. Okay, so previously we had seen this actually when we solve it, it comes to be 36i plus 9i squared minus 4 plus 4i plus I squared. Okay, so you take out the brackets and you also substitute for I squared is equals to minus 1. You have 36 plus 36i minus 9 minus 4 minus 4i, and this itself becomes minus 1. So minus 1 and minus, so you have plus 1. Okay, so then if you take all the real numbers to one side, you have 36 minus 9 minus 4 plus 1. Okay, and you have 36 minus 4 I. Okay, and you get 24 plus 52i. And if you take out the highest common factor out of it, so that is 8 plus 4i. Okay, so this is the solution that we get for when you are given Z1 and Z2, and you can, if you are asked to find the if you have to solve it with in the identity or in the general form of the identity Z1 square minus Z2 square. So this is how you can use the identity to get your answer. Okay. Now let's see little different or where we are introducing um, a third complex number. Okay, so actually this will be Z3. Okay, so now let's see how we can prove this. So if you have Z1 plus Z2 plus Z3 squared. Okay, so you write the individual terms in the form of products between the bracketed terms. Okay, so Z1 plus Z2 plus Z3 multiplied by Z1 plus Z2 plus Z3. Okay, so now again by using distributive law that we had seen for multiplication of multiplication of complex numbers. Okay, so you have Z1 plus Z2 plus Z3 multiplied by Z1. Okay, and then you have plus Z1 plus Z2 plus Z3 multiplied by the second term over here, and plus Z1 by Z2 by plus Z3 multiplied by Z3. Okay, so now you expand them all. We have Z1 square plus Z2 Z1 plus Z3 Z1. Okay, then you have plus Z1 Z2 plus Z2 squared plus Z3 Z2, and then you expand the third and the last third and the last part, the third and the last term. We have Z1 Z3 plus Z2 Z3 and plus Z3 squared. Okay. Now, since we already know that, if you write Z1, Z2 is going to be equal to Z2, Z1, and similarly Z2, Z3 is equal to Z3, Z2, and Z3, Z1 is equal to Z1, Z3. Okay, so this is based on the commutative law for when we find the product of complex numbers. So over here, we will take all these similar terms together. So you can first write down all these squared terms on one side for ease. So Z1 squared plus Z2 squared plus Z3 squared. Okay, then you have two of these similar terms. So you have two Z1 plus Z2. Then we have Z2, Z3 and Z3, Z2. So you can write it as 2 Z2, Z3 and plus you have Z1, Z3 and you have Z3, Z1. So again, this is they are the same term. You have 2 Z1, Z3. Okay, or you can write it like over here. They are asked, they prefer it as Z3, Z1. Okay, so Z1. So this is equals to your RHS. Okay, so this is your LHS, and you can see that it is hence. So hence, note. Okay, so you can see that similarly, if you keep increasing the increasing the number of complex numbers in the bracket, and you try to find uh, uh, find the solution or try to see how the identities change with increasing complex numbers or increasing the powers of the bracketed expressions. So you can solve by yourself also and see how it will change. Okay. So over here, we mostly use the distributive laws and commutative laws of when we have the multiplication between two complex numbers. So the identities are mostly based on the products or the finding products for the complex numbers. So let's see an example for this identity also. So if you have z1 is equals to 6 plus 3i and z2 is equals to 2 plus I, and if you have z3 is equals to z3, we will take as 1 plus I. Okay, so let's take these as the examples, and we will try to solve and we will try to see what is z1 plus z2 plus z3 squared. Okay, so let's solve for this. Now, we know, okay, we know that z1 plus z2 plus z3 squared is actually equal to z1 squared plus z2 squared plus z3 squared plus 2z1 z2 plus 2z3 plus 2z3z1. Okay, so we know this. So now let's substitute directly for the expanded identity. Okay, so z1 squared, so that is, so what you have is x plus 3i squared. You have z2 squared, so that is 2 plus I squared. Then you have z3 squared, so 1 plus I. Okay, and the next term is 2z1 z2, so 2 6 plus 3i 2 plus I plus you have 2 z2 z3, so 2 z2 z3, and then you have twice of z3 z1. Okay, so 2 z3 and z1. Okay, so now let's expand the square terms that we have, and also do the multiplication for the rest of the terms. So we get this as 36 plus 36i plus I squared. Then we have 4 plus 4i plus I squared. And over here we get this as 1 plus 2i plus I squared. Okay, now you expand or you find the products between the z1, z2, z2, z3, and z3, z1. So 2 we keep outside for now, and we expand it. So you get 12i plus 6i plus 6i plus 3i squared. Okay, then you have plus over here 2. So you have 2 plus I plus 2i plus I squared. And then for the last term, you have plus 2, 6 plus 6i plus 3i plus 3i squared. Okay, so now we substitute for I squared is equals to minus 1 for all the terms that we have in the bracket. So what you get is 36 plus 36i plus 9i. Okay. Oh, sorry. This would be 9i squared over here. And then, yeah. So 36i over here, this becomes minus 9. You get The next one you have 4 plus 4i, this is minus 1, then plus over here, if you get minus 1 over here, so minus 1 and 1 gets cancelled, so what you're left with is 2i. Okay, and now expand this, you get 24. This is actually not 12i, this is just 12. Yeah, so this is 12 plus 6i. So you expand, you multiply 2 for the rest of the 3 terms that we have. Okay, so you have 24 plus this is already 12i, so 24i, and this becomes minus 3 since I square is equals to minus 1. So minus 3 into minus 2, you have minus 6. So I'm writing the next terms below here. So you have plus and you have 4 plus over here I plus 2i, you have 3i, so you have plus 6i. Okay, so you have, yeah, so this is your plus 3i to 2, you have 6i, and this again becomes minus 1, so this is minus 2. And then for the next bracket, you have 12 plus you have 6 plus 3i, you have 9. So 9 into 2, so you have 18i. And over here, then this is minus 1, so this is minus 3. Minus 3 plus 2 is, minus 6. Okay, now we try to do what we've done before. So we take all the real numbers to one side. So we have 36. A minute. Okay, so you have 36. Over here you have actually minus 9. Yeah, so you have minus 9. Okay, then you have plus 4. Over here minus 1. And then you have plus 24. Okay, and then minus 6. Minus 6, and then you have plus 4 again, minus plus 4. Okay, then you have minus 2 plus 12, and then lastly you have minus 6. Okay, minus 6. So I'll just write the real part here. So this is 56. Okay, so the real part. Now for the imaginary parts, you have 36i. Okay, so if you just write it as 36i, then you have plus 4i, and then you have plus 2i, or if you actually just write the I outside, becomes easier right now. So 36 plus 4, and then you have plus 2 over here. Okay, so plus 2, and then you have plus 24i. So 24 plus 24, and then you have 6i plus 6i and plus 18i. So plus 6i plus 18i. Okay, so that, okay, so now if you add it up, so you have, so you get 36 plus 4 plus 2, 24, 6 plus 18. So you get this as 90. Okay, so this is what you get. So this is what you get. Now, if you want to reduce this further, so either you can reduce it if you get the highest common factor of it, or you can just leave it at this also. So this is what we get when we have when we want to find when we have three complex numbers and we want to find the answer to the identity of adding up all three complex numbers and squaring the entire thing squaring the entire thing using the identities that we can easily prove. So if you take the let's see what would happen if we take the negative of the three complex numbers. Okay, so if we have Z1, Z2, and minus Z3 squared. Okay, so let's see what is the answer for this identity. If we want to simplify this kind of an expression, what would be the final identity that we can use in the general form if we want to, solve a few examples. So you can write this in the form as we have seen before: Z3, Z1 minus Z2 minus Z3. So these are very simple in a way. You can do these on your own, but like you can understand, like if you get sums which are in this form, you can easily apply the identities and you do not have to go through the entire, the expansion process that we do. So let's see how we can solve this. So you have Z1 minus Z2 minus Z3 and multiplied by Z1 minus Z1 minus Z2 minus Z3 Z2 minus Z1 minus Z2 minus Z3 Z3. Okay, so let's expand all and see what we are left with. So you have Z1 squared minus Z2 Z1 minus Z3 Z1. Okay, over here you keep the minus sign in mind. Okay, so now we have to keep in mind that there's a minus sign between the terms over here. So you have Z1 Z2. Okay, and then you have minus Z2 square, so this again becomes plus. Okay, Z2 square, and you have minus Z3 Z2. So you take it out and you get that as plus Z3 Z2. Okay, so you can see that there is kind of a difference in the how we had solved it when all the operators here were for a sum. Now the last bracket that we have, so you have minus Z1 Z3. Okay, and then over here you have minus Z2 Z3, then this will become plus. So you have Z2 Z3. Okay, and then finally you have minus Z3 squared, then with the negative sign outside the bracket you have plus Z3 squared. Now since obviously Z1 Z2 is equals to Z2 Z1 and it applies for the different complex numbers, so we can write this as Z1 squared. Okay, let's take all the squared terms on one side. Okay, plus Z3 squared, and then you have Z2 Z1 and Z1 Z2. So there's a negative sign, so this will be minus Z1 Z2. Now for you can see that we have Z3 Z2 and Z2 Z3, but over here your sign changes. Okay, so you have 2 Z2 Z3, and then you have minus Z3 Z1 and minus Z1 Z3. So that would be again minus 2 Z3 Z1. Okay, so you can see that you can simplify this expression in terms in like the identity form, and this is the identity that you get. So let's write it in the final form. So you have Z1 minus Z2 minus Z3 squared is going to be equal to Z1 squared plus Z2 squared plus Z3 squared minus 2Z1 Z2 plus 2Z2 Z3 and minus 2 Z3 Z1. Okay, so this is your final identity, and we have proven how or we have shown how we get this final identity. Okay, so let's kind of solve for the for this identity using the similar example that we are taking, 6 plus 3i. And you have z2 is equals to 2 plus I, and z3 is equals to 1 plus I. Okay. So we want to find what is the solution for this. Okay. So we will use this identity. Okay. So we have z1 square plus z2 square plus z3 square minus 2 z1 z2 plus 2 z2 z3 and minus z3 z2. So we'll quickly write it in the expanded form itself, for these. So you have z1 square plus you have z2 square and plus you have z3. So you have z3 square. Okay. Then if you remember, you have minus z1 z2. Okay. So minus 2 z1 z2. So you have minus 2 6 plus 3i and z2 plus I. Then you have plus z2 z3. Okay. So 2 plus I and 1 plus 1 I. And then again you have minus 2 z3 z1. So 1 plus I and 6 plus 3 I. Okay. So let's expand them all. 36 plus 36i plus 9i squared. Then we have 4 plus 4i plus I squared. And then you have 1 plus 2i plus I squared. Okay. And then you get 2 and you multiply these two complex numbers and you get 12 plus 6i. Sorry. Yeah. 6i plus 3i squared. Okay. Then the next would be 2. Over here you have 2 plus I, and then you have 2i plus I squared. This will be plus. Okay, and then again minus 2. So you have 6 plus 6i plus 3i and plus 3i squared. Okay. You substitute for I squared is equals to minus 1. So 36 plus 36i minus 9 plus 4 plus 4i minus 1. Over here, I squared becomes minus 1, so you can cancel out 1 and minus 1, so you're left with 2i. Okay, now you expand, multiply 2 for all the bracketed terms, so you have 24. This would be 12i, so this would be minus 24i. Okay, and then this will always already be minus 3, so minus 3 minus 2, so you have plus 6. Then you have 4, then this is 3i, so plus 6i, and this is minus 1, so you have minus 2, and it is yes. So over here you have minus 12, and this is 9i, so minus 18i, and this becomes minus 3, so minus 3 minus 2 is plus 6. Okay, so now again what we do, we take all the real numbers on one side. So 36 minus 9, you have plus 4, and then you have minus plus 4, then you have minus 1, and then you have minus 24. Just wait a minute. Okay, yeah, so we have 36 minus 9 plus 4 minus 1 minus 24. Okay, then you have plus 6 plus 4. Okay, and then the last you have minus 2 and minus 12, and you have plus 6. Okay, so plus 6. Okay, so just let's check if you've written all the ones. So 36 minus 9 plus 4 minus 1 minus 24 plus 6 plus 4 minus 2 minus 12 and plus 6. Okay, so we've written all the real terms on one side. I'll just quickly solve this and write it down. One more. So this comes to 8. Okay, now let's write all the imaginary parts. Okay, so you have 36. Okay, 36 I. So we'll write the I outside the bracket. Okay, so you have 36, then you have plus 4. Okay, then you have plus 2, and you have minus 24, and you have plus 6 again, plus 6. You have lastly minus 18. Okay, so minus 18. So this is the imaginary part. Okay, so solving this, we get as 6i. Okay, so now if you reduce it, you get 6, 4 plus 3, 5. Okay, so you can see how we all also found the solution for this expression using the identity form. Okay, so using the identity that we had, derived, z2 minus z3, the whole square is z1 squared plus z2 squared plus z3 squared. Since we have the minus sign, so the first term we have like minus 2 z1 z2, but we have plus 2 z2 z3, and we have negative term again as z3 2 z3 z1. Okay, so we have used this identity and we found the solution or the answer for this expression. So today we have seen the identities which are actually the square of the say two complex numbers or three complex numbers. In the next class we will see how we can prove and also derive for cubes of the sum or the difference of two complex numbers, two or three complex numbers. So we'll see how we can derive those and also prove those, and we will solve examples for each of the identities that we prove. So thank you for attending this class, and see you in the next one.